right. Let's go ahead and get started. If more people show up, I'll let them in. Hi, everybody. Thanks for spending your Tuesday night with me. So just so we can go in kind of order, if this is okay, let's start with any questions about multiple choice or any sort of themes or content or topics that you want to talk about that showed up on the multiple choice, just so that we don't have to keep flipping back and forth between whole bunches of paper. I don't have my stylus on me, so I'm not going to be able to write on the screen, but I should still be able to point and talk about stuff. Ooh, look, lots of people. It's a party. All right. Who wants to go first about something on the multiple choice?
I actually have a lot of questions from the multiple choice.
Okay.
So on number 4, I wasn't sure like the difference between B and D.
Number 4. Okay. So we did this question in class, I think. The difference between B and D is that it says that the whole point for making the chromium oxide on the surface is to make sure that the iron underneath doesn't get rusted. And so the difference between B and D, the surface models look pretty much the same, but in D's interior, it shows oxygen down in there. There's like an oxygen there, there's an oxygen there, there's an oxygen there. And so if the point of putting the chromium there is to make sure that the oxygen doesn't get in, this is not showing what we want. We would want it to look like B, where we don't see that oxygen infiltrating the interior of the metal.
And then I had a question about number 6. I was confused by when it said that it's harder because it said that the answer was C.
Yep.
And it says that because it's smaller, it's harder. I thought if it's smaller, if it moves more easily, wouldn't that make it more bendy?
So having the copper atoms inside of that alloy is actually going to make it less bendy. Let's see if we can find a picture somewhere that shows something like this. Okay, so if you flip the page real quick and you look at number 8, this picture from A would be similar to what would be happening, where those larger atoms would be is it silver? No, gold. So those larger atoms would be gold and those smaller atoms would be copper. So if those smaller atoms are sort of stuck in there, it's going to make it harder to get those other atoms to slide against each other, because it's sort of going to jam up the works. It's going to get in the way and they're not going to slide against each other as easily. So that would actually make it harder.
And then on number 11, I just wasn't sure how to do it.
Okay. Oh man, this is when I wish I had my stylus. I wonder. No, it's not going to work because I don't have the right program on this computer. So what's going on number 11 is it specifically tells us we're at 0 Celsius and 1 atmosphere. And so we know that that's at STP. And so one of the shortcuts that we know about STP is that at STP, 1 mole of any gas takes up 22.4 liters of space. And so if I have 2 liters, if I convert 2 liters into moles using that conversion of 22.4 liters, I've got about 0.1 moles of gas. So I can go through these 5 choices and figure out which one is going to give me about 4 grams in 0.1 moles. So if it's 4 grams in 0.1 moles, that means 1 mole is about 40 grams. So the molar mass would be about 40 grams.
So I use Stoich for that.
Yeah. But it's a lot of rounding numbers that are really easy to not have to have a calculator for.
And then on question 19, I wasn't sure how to approach it.
All right, so this is about what makes gases act non-ideally or what deviate from the ideal gas law. And so there's technically three main things, kind of four, that can make gases not act ideally. So one is if we have a really low temperature. Another one is if we have a really high pressure. Both of those make gases act not ideally because it's getting closer and closer to acting like a liquid. So low temperature means those particles aren't moving as much. High pressure means that we're sort of decreasing the space between those particles. Two other things. One of the main ones is causing intermolecular forces to happen. So whether that's because I'm at a low enough temperature now that those atoms are able to stick together, or whether it's because I've got a much larger, more polarizable molecule that's allowing those intermolecular forces to happen. Another thing that can make those intermolecular forces happen more often is just by having a physically large molecule that takes up a lot of space. So in this case, if I've got more pressure, that means I'm actually getting more collisions with the container than I expect, which is going to happen because those argon atoms are pretty big. And so if they're taking up more space than we expect them, that means they're going to be bumping into that container more often.
And then right below that, for number 20, what is particle volume?
This is exactly what I was talking about. This is like the size of the atom itself.
Okay. And then number 23, I wasn't sure what the difference between bonding and non-bonding pairs.
So bonding pairs are the electrons that are actually physically involved in the bond. And the non-bonding pairs would be the lone pair electrons.
And then number 26.
So I have a problem with number 26. I think both A and B are true.
Okay, because I was gonna ask like what the difference was between those two.
Yeah, I'm sure that they're trying to get at something in that question, and I'm just not quite sure what. This is I'm not quite sure where that question is going. I think A and B would both be okay answers. Go ahead and ask one more, and then we're gonna give somebody else a chance. Okay.
Okay. Number 46.
46. Yes. Okay. So what's going on is I basically have two separate containers of two separate gases. And then by pulling out that divider, I'm giving those gases now twice as much volume to be able to move around in. So if I am doubling the volume, that means I'm cutting the pressure of each one of those gases in half. That also means that when I add those two pressures together, the total pressure is going to be half of what they were added together when they were separate.
Okay, thank you.
Yep. All right. Anybody else have some multiple choice questions or topics they would like to clear up?
Could we do number 44?
44. All right. So 4 different gases, they're all at the same temperature. The samples are in 4 identical rigid containers. So it means the volume is not going to change. On the basis of the data provided above, the gas in container 3 could be, all right, so we've got same volume for everything. We've got pretty close to the same pressure for everything. Is 64 the molar mass of SO2? 32, yeah, should be pretty close. So we're saying in these identical containers with a pressure around 1 atmosphere, the mass of those samples is about 1 mole. So if this is 16, then the gas should be something where the molar mass is close to 16. So would that be CH4?
Okay, thank you.
Yep. A lot of times when they give you these problems where they give you a table to compare, you've got to sort of narrow down what variables they're changing and what variables they aren't changing. So when I read this question, I noted that the gas was the same for all, or the temperature was the same for all of those gases. They're in identical rigid containers, meaning that their volumes are all exactly the same. I can look and see that their pressures are all the same. If temperature, pressure, and volume are all the same, that means however many moles they have in there also have to be the same. So there's a lot of questions like that.
Can you please go over numbers?
Oh, go ahead, Nellie.
Can you please go over number 76?
76. Ooh, starting to dig in deeper. All right. Oop, went right past it. 76. All right. So we've got Maxwell-Boltzmann distribution of 2 different gases at the same temperature. So gas A and gas B are at the same temperature. We want to know which gas has the greater molar mass. So by looking at these graphs, I can see that the average speed for A is much lower than the average speed for B. Excuse me, I have hiccups. If that speed is lower, that's most likely to be the heavier gas. So gas A would be the greater molar mass than B would, because B is moving faster. That means it has to be a lighter molecule.
What does it mean by fraction of molecules?
It's basically a count. So sometimes these graphs say fraction of molecules, sometimes they say number of particles. It could say percentage of particles or percentage of molecules. It's all talking about how much of that sample is moving at that particular speed.
Thank you.
Yep. What else? We got more multiple choice?
Could you do
Could you
93?
Oh.
Keenan, what'd you say?
Could you go over 93?
93. All right, so this one, we didn't specifically use these graphs like this, and so a little bit of extra information might be more useful. AP has said that you don't need to know how to read these graphs anymore. So I didn't teach them to you. But what's going on in these graphs is that line P, this is where we have a gas, or sorry, where we have a solid because it's a lower temperature. Q is the amount of energy needed to change from the solid to a liquid. R is where we have a liquid. S is where, zoom in on this guy a little bit. S is where we're converting from a liquid to a gas, and then T is where we have a gas as our only phase. So basically what they're asking is, why does it require less energy to melt something than it does to boil something? And so the difference happens because when we're melting, we're only rearranging and breaking a few of the intermolecular forces between those particles. But when we are converting from a liquid to a gas, all of those intermolecular forces have to be broken. And so that requires much more energy. So that goes to A. The fact that intermolecular forces are completely overcome during that vaporization, that conversion from a liquid to a gas. Caroline, did you have a question?
Yeah, could you go over number 87, please?
87. All right. So 4 liters of helium, 6 liters of nitrogen, 10 liters of argon, all at 0 Celsius in 1 atmosphere, are pumped into an evacuated 8-liter rigid container. Ooh, so we got to do a decent amount of math here. So if I'm going from all of these, I'm changing my volume from my initial samples to when I'm mixing them all together. So anytime that I'm going to change that volume, I'm going to change my pressure also. So if I'm going from 4 liters of helium at 1 atmosphere, this would be like a P1V1 equals P2V2. Grab some scratch paper real quick so I can draw this out for myself. And remember, no calculator on this. So 4 liters of a gas at 1 atmosphere goes to 8 liters, and I want to know what its pressure is going to be for that helium. So I'm doubling the pressure. Remember that pressure and volume are inversely proportional. So I'm doubling my pressure, which means I'm going to halve my pressure. So my pressure of helium is going to be, instead of 1 atmosphere, it's going to be 0.5 atmospheres. If I do the same thing for the nitrogen and the argon, so nitrogen, I'm going from 6 liters and 1 atmosphere to 8 liters and I don't know what. So that's going to be 6 divided by 8. That's 3/4, that's 0.75 atmospheres. And then the same thing for the argon. I got 10 liters of argon at 1 atmosphere, and I want to know, if I move that to 8, what that pressure is going to be. So 10 divided by 8 is 1 2/8, which is 1 1/4, which is 1.25. So now I have helium with a pressure of 0.5 atmospheres, nitrogen with a pressure of 0.75, argon with a pressure of 1.25. If I add all that together, I should get 2.5 atmospheres. So that's a lot of work for a multiple choice question, because you're basically doing 4 whole calculations. You're doing 3 combined gas law P1V1 equals P2V2 calculations, and then adding all of those pressures together.
I didn't do all of that,
Be careful.
but I got the right answer.
Right.
Lasky,
Yes?
did you not hear what I said?
I didn't hear what you said, I'm sorry.
Oh, I didn't do all of that work.
What'd you do?
What I did, I added the 4 liters, the 6 liters, and the 10 liters. I did the combined gas law. So I did the 20 over 273 is equal to the 8 with the question mark to find the pressure over 273.
So say that again. So,
So
20 liters
Yeah,
over
273.
Okay.
And then I set it equal to 8 over 273 with the question mark next to the 8 representing the final pressure.
Oh.
And that was a lot easier than what you just said.
It would be a lot easier than what I just did. I think that's a sheer luck thing, though, Alex.
Oh.
Only because we really can't add those volumes together because they're 3 separate gases. And when we plug things into that combined gas law, we're not combining things. We're talking about a gas changing over time. So pretty much you and I did the same math. Like the algebra of it will work out the same. I just did it in 3 separate steps.
Right.
But I'm worried that if it was different numbers, it wouldn't work out.
Okay.
I mean, no, the math of it would still work out. It makes me nervous adding together liters because we never add together liters any other time. So just be careful of that. Like if you wrote that down on your test, I wouldn't count you wrong.
Okay.
I know, you're frustrated.
Nothing new.
I just don't want you like adding together volumes on other kinds of problems.
Okay.
Did you get what I'm saying?
Yeah.
Okay.
Okay.
Right. What else we got?
I just had a couple like general questions.
Okay.
Do we need to understand dipole-induced dipoles, or is it just dipole forces?
So dipole-induced dipole is probably not super high on the list.
Okay.
Just that you understand that if something non-polar is around a dipole, the dipole can sort of influence it enough to be able to make a dipole. I would be more interested that you knew about like ion dipole than the dipole-induced dipole guy.
Okay.
But technically all of them are fair game. Just the induced dipole is much more rare.
And then for intermolecular forces, do they only apply to solids and liquids and then not gases?
So we make some pretty serious assumptions that there are no intermolecular forces in gases, that those particles are moving fast enough and there's enough space between them that they're not going to be attracted to each other. Intermolecular forces can happen in gases. They just don't happen, the number of attractions are much smaller than they would be in solids or liquids.
Okay, that's all. Thank you.
You're welcome.
Can we go to number 60 on the multiple choice? I'm like confused about the partial pressure stuff.
60. That question that we just did with the argon, the nitrogen stuff, that's a partial pressure question too. So this one is similar. So we've got 3 smaller containers of gas, each at a liter. And they each are going to have their own pressure. They tell us that the ratio of the numbers of particles or of atoms in the vessels are 2 to 1 to 6 respectively. If they all have the same volume and the same temperature, that means that's also going to be the ratio of our moles, which means that's also going to be the ratio of our pressures, because everything else is being held constant. So if argon has 2 atmospheres, neon has half as many particles, so its pressure is also going to be half. So neon would have a pressure of 1 atmosphere in that 1 liter container. Helium has 6 times as many particles as neon, so its pressure is going to be 6 atmospheres. Now, when we start mixing those together in this 2-liter container, because we're changing the volume of the containers, the pressure is going to change. So for each one of these, from going from 1 liter to 2 liters, we're doubling our volume, which means we are going to halve our pressure. Our pressures are going to be cut in half. And again, that's that relationship from P1 V1 equals P2 V2. So instead of it being 1 atmosphere pressure of argon, it's going to be 1. Neon is going to be 0.5 atmospheres, and helium is going to be 3. So 3 plus 1 plus a half gives me 4.5.
Could I just add all those together and then divide by 2? That work too?
You could do that too, yeah.
Okay,
That's sort of what Alex and I were just arguing about.
Okay, thank you.
Could you please go over number 92?
92. Okay. So this goes back again what we were talking about a little bit earlier about what makes things either behave ideally or non-ideally. Most like an ideal gas means that we want high temperature and a low pressure if we can help it, and we also want smaller molecules, smaller particles. So they're mostly all at the same temperature. Ammonia is at a little bit higher temperature in E, but it's got a really high pressure. We don't want high pressure. Hydrogen in part A has a really low pressure and a warmer temperature. So those two put together are going to give us the most ideal conditions. And it's a bonus sort of that we've got hydrogen gas, that those particles are so small because they're not going to take up much space. They're not going to be very polarizable. They're not going to be able to form very many intermolecular forces.
Can I ask a question about the ideal gas?
Yeah.
Okay, so you want the lightest mass because if they're too big, they can stick together.
Mm-hmm.
So does that apply for non-polar molecules as well?
Yes. So way back when we first started talking about our intermolecular forces, we talked about this idea of polarizability, where when we talk about London dispersion forces, even if something is not polar, the bigger the the bigger the size of the molecule.
Are you sure it's size?
I'm slowing down to make sure I'm saying the right thing. The bigger the size of the molecule, the more surface area we have.
Okay, yeah.
And so it's more likely to bump into something else and stick. And also, when we get into larger by size molecules, they also have more electrons in them because they have more electron rings, which means they're more polarizable. Those electrons are floating around more, meaning that they can do they can smush more to one side or the other to make a dipole force.
Okay. So that will give it a lower pressure because they're sticking to each other rather than hitting off of the sides of the container?
Yes.
Okay.
So that would make it behave non-ideally.
Okay. Cool. Thanks.
Yep. I'm so careful about saying size and mass now, Alex. You got me trained.
Especially around me.
I had a question about number 10.
Number 10.
I'm just confused about the reasoning behind it.
Okay. Way back up to number 10. Oh, okay. So they tell us that sodium sulfate is a better conductor of electricity than sodium chloride when they're dissolved in water. I'm going to tell you right now, this is not going to show up on your test tomorrow. This is
Okay.
more related to what we're going to talk about next chapter, but it's because sodium sulfate breaks up into more ions
Oh, okay.
because it's 2 sodiums and 1 sulfate, so that's a total of 3 ions.
Okay, I
And
gotcha.
sodium chloride is only 2.
And I had one like for 15 and 18, it's kind of the same thing. So when ionic solutions in aqueous solutions, does that make them conductive?
Yes, so ionic substances only conduct either when they are melted into a liquid, which we don't have like liquid salt very often, but it can happen, or if they're
Okay.
dissolved in water.
Okay.
Metallic
Thank
ones
you.
are going to conduct electricity all the time,
Okay.
and covalent substances are never going to conduct electricity.
Got it.
Anything else on the multiple choice? We can talk about the free response too. We can talk about stuff from the example problems in the packet. We can talk in stuff in general. Anything that you guys need.
I had one general question
Okay.
about what makes speed increase and what makes kinetic energy increase.
Kinetic energy is only controlled by temperature.
Okay.
That's it. So if I increase the temperature, I'm going to increase my kinetic energy. I decrease the temperature, I'm going to decrease my kinetic energy. I have 2 samples. Doesn't matter what they're made out of. If they have the same temperature, they have the same kinetic energy. Speed is controlled by temperature and molar mass.
Okay. And that's when the molecule's heavier, the speed will be lower.
Correct.
Right. Okay. Thank you.
You're welcome. I know that's hard to think about because we don't talk about kinetic energy in everyday life very often. We're much more used to talking about speed. And so it's hard to think about something that we don't ever measure in real life.
I have a question about ion dipole forces. So
Okay.
if you're given a molecule, like just a compound, how can you tell if it has ion dipole?
So ion dipole is not going to happen in one substance. It's going to happen between 2 different substances. So I thought there was a question. On your multiple choice. I'm going to keep talking while I look for it. So an ion dipole force would be something like dissolving an ionic substance in water. Because water is polar, even though it does have hydrogen bonding, I understand that. But the more positive side of the water molecule is going to be attracted to the negative ion. And the more negative side of the water molecule is going to be attracted to the positive ion. Nope, I guess not.
So it's gonna like tell you 2 different molecules, and you gotta determine if ion dipole forces can happen between them.
Yeah. So, and what I've seen on a lot of times on AP questions. So this is at the beginning of your packet. So this sort of shows what's going on. So the hydrogen end of the water molecule, which is more positive, is attracted to the negative ion. And then the more negative side of the water molecule, the oxygen, is attracted to the positive ion. I've seen cases where like they put a picture in the question of a calcium ion. And then it's like, draw a water molecule arranged the appropriate way of how it would be attracted to this calcium ion. And so you'd have to go, well, okay, so that's a positive ion. I need to draw this so that the oxygen end of the water is attracted towards that positive ion.
Okay, thank you.
Yep.
Can we go to page 27 in the packet?
Maybe. Oh, that's all the way at the end. Yeah. Okay.
Okay, so it's up at number 57. I guess
Okay.
it's not the same for yours.
Because I took up some space with the answers, so it's fine.
Okay. So I get the problem. I just don't get why when the molar mass is bigger, it'll be closer to the one with the bigger molar mass.
Okay. So this has to do with what Brady was just talking about speed.
Okay.
So if I have these two cotton balls in here, notice that it says volatile, right?
Mm-hmm.
So volatile means something that's really easy to turn into a gas.
Okay.
Volatile things are usually really stinky because we can smell the gas particles. They evaporate really quickly.
Yeah.
And so these two chemicals are going to let their gas particles start bouncing around in this tube. If this base, so if we look at this first one, so CH3NH2, 14, 26, 27, 28, 29, 30, 31. So it's got a molar mass around 31.
Yeah.
HCl has a molar mass around 36 and a half.
Yeah.
Right? If that base has a smaller molar mass, we assume that these are the same temperature because they're sitting in the same test tube together. If it's got a lower molar mass, it's going to be able to travel faster at a higher speed than the HCl would be able to. So where they finally meet up is going to be closer to the HCl side, because if that HCl is moving slower and the base is moving faster, it's going to be able to get closer to that HCl where they're going to start to react.
Oh, okay. That makes sense.
So there was a multiple choice question about this too on your practice, where it said which set would give you a reaction really close to the middle.
Mm-hmm.
So if we want the reaction closest to the middle, then we want the molar masses to be really close to each other.
Okay, that makes sense. Thank you.
I have a quick question about number 22.
On the multiple choice?
Yeah, on multiple choice.
Okay. My finger's gonna get really tired from doing all of this scrolling. 22, okay.
I was just confused why the answer is D because I expected it to be something like the pressure would be lower, like reading the question, but.
All right, so at a constant temperature, the behavior of a real gas. So when they say real gas, they mean something that's not acting ideally.
Okay.
More closely approximates that of an ideal gas as its volume is increased because so this goes back to all of those things about what causes gases to behave ideally or not ideally. If we increase the volume, we would be decreasing the pressure. That's true. But that's not going to necessarily make it act ideally or not ideally. That's just a relationship between all gases.
Yeah.
the reason that that works out is because if the distance between those molecules is greater, they're not colliding with each other as often, they're less likely to have intermolecular forces with each other, all those things that are going to stop it from acting ideally.
But why would the average distance between molecules become greater?
Because we're increasing our volume. So we've got the same number of particles, but now they have more
Okay.
space to bounce around in.
Okay,
So that on average, they're not going to be as close to each other.
gotcha.
I have a question about the free response.
Okay.
It's number 11.
Okay.
Okay, so it's the second part, and it keeps saying like H2 produced in the reaction would have if it were dry. So how would I figure out, like, I don't even know what that means.
If for D, okay.
Yeah, C and D.
So if it were dry, means that we have to subtract away the vapor pressure of the water.
And it's just the pressure.
So yeah, so in C, they give us the vapor pressure of water at that temperature, and we know the overall pressure is 749 torr. So 749 torr minus the vapor pressure of the water is going to give me just the pressure of that hydrogen gas. So
Okay.
saying it is dry is because we're taking away the water pressure.
And that's all we're doing.
Yeah. And so then in
Okay.
D, when we do Puvnert, we're going to
We're just gonna
use
use
that
that new
728
pressure.
as our pressure.
So like if we weren't given C, then you just do the same thing.
Yeah.
Okay.
Go ahead and subtract away that vapor pressure of water before plugging it into Puvnert.
Okay.
For the first one on free response, could you go over how to set up the stoichiometry for that?
Yeah. So this is a pretty classic gas law stoichiometry where they give us all of this information about the oxygen, but they're asking us to calculate the answer about a different chemical, about the hydrogen peroxide. So since we know the volume, the pressure, and the temperature of the oxygen gas, we can plug that into Puvnert to find out how many moles of oxygen gas we have. And then we can use that moles of oxygen as the beginning point of our stoichiometry. In this answer key, I copied this out of the official answer key. I wouldn't split this up into multiple steps. I would just do it as one long dimensional analysis. So I'd start with my moles of oxygen, do my mole ratio to get to moles of H2, O2, and then, so this is a step that I wouldn't ask you to do on the test because we haven't talked real hard about molarity yet. But molarity is moles per liter, so we can use that as a conversion factor to go from moles to liters. So if I was going to work it out, I would have strung all that together. Any other questions? Back to the multiple choice or questions in general, free response, anything.
I had a question about number 84 in the multiple choice.
Okay.
How do you find that?
Some of the question is like, how does this even work? Okay, so this is going back to that same idea of, it says, which of these situations is the gas expected to behave most like an ideal gas? So when we want gases to behave like an ideal gas, we want them to not have any intermolecular forces. We want them to not be interacting with each other at all. And so the conditions that give us that the best are high temperatures, because it's making those gases move around really fast, and low pressures, meaning that those particles are not being condensed together at all. So highest temperature is the 500. Between those two, C would be best because it's got the lowest pressure of the highest temperature.
That makes sense. Thank you.
Yep. Stupid hiccups. What else we got, y'all? Or your brains just mush at this point?
Very much mush.
Can we go on number 4 on the free response, please?
Number 4. Yes. What about it?
I was just confused on how to explain it, like for specifically part B.
So if they ask you to justify something about higher boiling points or melting points or vapor pressures or any of those sort of things, we got to talk about strength of intermolecular forces. So both of these substances, which this is kind of an old question. I don't think they would make you draw these without some sort of hint as to how the structures would be different. Both of these are nonpolar molecules. Sorry, I forgot my words. And so they're both only going to have London dispersion forces. But the shapes of them are very different, right? So in N-butane, we've got this nice straight chain of carbons. And in isobutane, we've got this weird like branchy thing going on. Because of this branchy thing, this actually minimizes the surface area. So N-butane has a larger surface area, so it's got more chances to be able to make those intermolecular forces with other particles, meaning it would have a higher boiling point. So that's something that, like way back when we talked about polarizability, right? So because this one has more surface area, we're able to access those electrons a little bit easier. It's going to have a higher boiling point.
Okay, that makes sense. Thank you.
Anything else?
On number 29 on the multiple choice, it's talking about carbon chains and why it's harder to break longer carbon chains.
Yep.
I was wondering what we need to know about that, or if we need to know why.
So this is similar to what we were just talking about on that free response question. So since the nonane has a much longer chain, it's got more surface area. So it's going to have a higher boiling point because it's going to have stronger London dispersion forces.
Okay.
And in this case, they're showing us trifluoropentane as the other substance, even though it's got those fluorines on there and it's polar, because it's not 100% symmetrical. They're telling us, bam, here's the boiling point.
Right.
So these London dispersion forces are stronger even than the dipole forces that trifluoropentane has.
Okay, makes sense. Thank you.
Hey, look, Alex, it's size versus molar mass again.
So like surface area is related to like how strong the IMFs are?
Yep.
Okay.
Almost think about it almost like Velcro, right? So if you've got two little spots of Velcro and you're trying to get them to stick together, it's a lot harder. But if you've got big old fat pieces of Velcro, even if they're off center, they're still going to be able to stick. So it just gives us a lot more opportunities for those intermolecular forces to occur.
So like something with a hydrogen bond would have more surface area than something with just that, like
we really only worry about the surface area for London dispersion forces.
Okay.
Because hydrogen bonding is going to blow London dispersion forces out of the water in terms of strength.
Can we quickly go over number 28?
Yeah. Okay, oh, this has got lots of stuff. Okay. So methanol and ethanol, they give us the structures, they give us the formulas, they give us boiling point. So because we're talking about vapor pressure, right? So because based on the boiling points, we can see that C2H5OH has stronger intermolecular forces because it has a higher boiling point. That means it's also going to have stronger intermolecular forces, which reduces the vapor pressure.
Yeah.
So the equilibrium vapor pressure of CH3 is going to be higher because the intermolecular forces are greater in the C2H5 than those in the CH3.
Okay, thank you. I think it was just a bunch of wording.
Yeah, so we haven't talked about equilibrium a whole lot lately, but it doesn't, equilibrium just means nothing measurable is changing. So it means it's done evaporating, it's reached as much vapor pressure as it's going to have.
I'm confused about vapor pressure exactly. Like,
okay,
what causes that to increase or decrease, and like what is it generally?
So anytime, let me see if I can find a picture. This will work. So any liquid has a small number of particles, molecules that have enough energy to be able to escape that liquid and turn it into a gas. So when we talk about the Maxwell-Boltzmann distributions, the graphs with the curves, the majority of those particles have the main temperature, right? But some of them have a lot higher speed than some other ones. So those particles that have the highest speed are able to sort of pop off of the surface of the liquid. If I have a liquid that has really strong intermolecular forces, there's not going to be very many particles that are able to escape because those strong intermolecular forces are going to hold those particles in. If I have a high vapor pressure, I've got a lot of particles up here. It means I've got weak intermolecular forces. So really all we really use it for is a gauge of our strength of our intermolecular forces.
Okay, thank you.
Yep. All right, we got a couple minutes. Anybody got a last minute question?
Could you go for 51 on the multiple choice?
Yeah. I think I'll get my menu to go away. Did you say 51?
Yeah.
Ooh, see, there's that graph. So we've got distribution of molecular speeds for 4 different gases at the same temperature. So there's 2 different ways we can see these graphs. One way is this way, where we've got different gases, but all at the same temperature. And another way is to show the same gas, but at different temperatures. So it's always important to read that and make sure you know what it's talking about. So we can see that gas, I'm gonna call this gas A, right? Gas A has a rather low molecular speed because its peak is lower. And then gas B is a little bit higher, gas C is a little bit higher, gas D is it has the highest speed out of all 4 of those, highest average speed. If they're all at the same temperature, the only thing that can really be affecting the speed of those particles is their molar mass. So answer would have to be D. Pressure is not going to change their speed. Density of the gas is not going to change their speed. The volume is not going to change the speed. The only thing that can control speed is temperature and molar mass.
Okay, thank you.
You're welcome. All right. We're about done. We could take your silence as meaning that you are done. Everybody remember to take some nice deep breaths. Y'all are going to kick some butt on this test tomorrow. Don't cram so much that you make yourself crazy, and go to sleep. So says your mother, the chemistry teacher. All right. I will see all of you tomorrow morning in class. All right. Bye, y'all.
Thank you.
Welcome.
You're the best.
Thank you.